It's my pleasure to invite have Anthony Webster here at the Turing Institute to discuss his research. So just a brief biography of Anthony. So he joined the Nuffield Department of Population Health at Oxford in 2016 after a master's in applied statistics at Oxford. And he's changed career, interestingly, from physics to statistics. So following 2 years in the cancer epidemiology unit, he was awarded a fellowship from the Nuffield Department of Population Health to use big data and modern statistics to characterize and to classify diseases. So the next step in this work will involve genetic studies, and in 2022, he joined the Lindgren group, also at the NDPH, right, to work as a statistical geneticist, acquiring key skills for the analysis of genetic data. So Anthony's previous research includes theoretical and statistical studies of fusion plasma stability as a senior research scientist for UK AEA, and a PhD from the University of Edinburgh with Professor Mike Cates that studied the aging and stability of emulsions and foams. Right, okay, so Anthony's going to be talking about causal attribution fractions and the attribution of smoking and BMI to the landscape of disease incidence in the UK Biobank. So over to you, Anthony.
Okay, well, thank you very much for the invitation to speak here. And thanks also to Nuffield Department of Population Health for funding me to do the fellowship work that led to these results that I'm going to talk to you about today. Now, this is a topic that doesn't really win you any friends. If you're to the statisticians, this sort of work will not be data-driven enough, it will not be rigorous enough. To epidemiologists, it involves the C word, causal, and this immediately will lead to suspicion and uncertainty, skepticism about the results. So since we're sitting here in the Turing Institute in the middle of London, I felt almost obliged to mention this person, John Graunt. I don't know whether you've heard of him or not, but in the 1600s, he did the first data-driven big data study of the causes of ill health, or at least the causes of death. During the 1600s, there was a records of deaths were kept. I think they were kept here in the British Library, actually. And the purpose of these records was so that you could spot when there was an outbreak of plague. And this would allow people to leave the city and other steps to be taken. But what John Graunt realized was that you could use this data to establish what was actually causing people to die. And he tabulated this information and made various inferences based on it. Now, most of us haven't heard of him. I'm mentioning it because even in that first study, many of the problems we have today when we're doing epidemiology existed then. So how do you actually disease? Do you group together several diseases with similar symptoms, or do you split them up? You need enough cases to make it a meaningful study statistically. And so all these issues are there right from the beginning, and that sort of fed into some of my thinking. But of course, most of us hadn't heard of him. And one possible reason for that is because 25 years later, Isaac Newton came along and published his Principles of Natural Philosophy, which explained a lot of the data of the astronomical world in terms of a small number of formulae. And thinking for the next 300 years was then dominated by these sort of mathematical modeling as opposed to these data-driven approaches. So thinking about some of these issues, and also inspired by some simple models of cancer, I proposed this work to characterize and classify diseases by using big data sets that were becoming available and more than just conventional epidemiology, so clustering techniques and those sorts of things. And I focused on three main topics that other people were tending to ignore. One was classifying diseases using the age of incidence. The other was using similarity of risk factors. So the idea there was that if you have similar risk factors leading to a disease, then it is likely that you may have a similar pathway that's triggering that disease. And then finally, and the thing I got to last of all, was to sort of classify diseases by how modifiable they were in terms of exposures, because this would be important if you were looking to prevent disease. And this is what I'll talk about today. And so the aim was to determine which diseases were most modifiable by established risk factors. So at least this was my starting aim. Most of this talk will be about why I've done things as opposed to what specifically I've done. And I wanted to do this in as epidemiologically rigorous way as possible. Now, the reason for that is because I started off as a theoretical physicist. I then became involved in analyzing data. I then, when I joined the cancer epidemiology unit, I learned about epidemiology. And what my experiences taught me was that actually good data, bigger data, and practical, pragmatic approaches that are informed by knowledge of what's going on can often get you further than very advanced statistical or theoretical approaches. So I wanted to build in as much understanding as was already there into my analysis. Now, so what is epidemiology? Well, this is a recent quote. There are three core tasks of epidemiology: to describe health states, to predict outcomes, and to identify causes. In my view, a lot of epidemiology tends to be with characterizing and describing sort of health states. But this, in my opinion, epidemiology could be described as really the science of doing statistics and getting the correct answer, because in many ways that is really what it's about. So just to expand on this, if you gave a statistician some data, they would go away, they would check for outliers, explore correlations, standardize the data. There'd be some sort of model selection procedure that would be used. The epidemiologist, in contrast, would go away, they'd dig out the scientific literature, they'd look for confounders, potential likely confounders, they'd be interested in causal pathways, they'd consider how they're going to interpret results to get a meaningful answer. So to give another example, statistician is given some UK Biobank blood data. They go away, they run some principal components, and they can see two clear clusters, two clear groups. They delve a bit more into the data, and they find that the two groups are men and women. And when they look a bit further, they see that there's one single biomarker that seems to be driving this separation. Now, I'll be honest, I've done this. Now, the epidemiologist, of course, they'll read up on the data. They may have some clinical training, some understanding. They'll note that there are men and women present in similar proportions in data. And they'll also note that testosterone is one of the blood biomarkers. Need I say any more? But the statistician does very well if there's no prior knowledge. However, collected data are usually quite strongly biased by prior information of what is likely to be important. And for this reason, this is why the scientist or the epidemiologist tends to do better and avoid conclusions that would be obvious if you had that prior understanding. However, there are important exceptions. These include genetic data and hospital episodes, so few of the former really are fully understood just yet. And the latter, they include sequences of correlated outcomes with many complex causes that we don't really know how to model effectively at the moment. So these exceptions, they tend to be associated with big and complex data, where the big is usually the number of variables involved per individual, but it's difficult to get your head around. So that's why I tend to regard epidemiology as the science of doing statistics and getting the correct answer, or alternatively, how to do better than a graduate statistician without knowing very much maths. So just one final example, in case you're not entirely convinced: handedness and health. So a question that often comes up from time to time in the popular literature is whether left-handed people are healthier and live longer than right-handed people. And depending on how you analyze the data, this is a conclusion you may well reach. And the reason why you can reach these misleading conclusions is that in the past, left-handed people were encouraged or forced in some cases to use their right hand. So left-handed people tend on average to be younger. And of course, age is the strongest risk factor for any diseases. So you can very easily form the wrong conclusions. But where in the data would you get that information about this retraining people? So, so this is why it's worth delving into the literature and stuff. Okay, so that brings me back to the main topic of the talk. I'm going to talk about in three main parts. I'm going to introduce relative risks versus attributable fractions. The main part will be discussing what I actually did in terms of estimating these attribution fractions. And then finally, I'll give a sort of short summary of some of the results just to give you a flavor for what we find. And I'm going to get my caveats in early. Although the studies here involved established risk factors and confounding factors, so everything is sort of well known, any biologically informed clinical input is needed to check the causal and the statistical assumptions before forming any biological conclusions or modifying public health policy about a specific disease. So I'm not trying to tell you that these results are definitely the way they are, definitely correct. I will say what my assumptions are, and I will say what results I find under those assumptions. And from then on, it's for others to take away and look at in more detail. So this work got picked up whilst it was a preprint by New Scientist. And David Cox did a really, really great job. So if ever you want somebody to write an article, I really recommend this guy. But a few weeks after this article arrived, to my great surprise, there came an internal email with a very similar study in sort of spirit, but for a Chinese population. So 500,000 people in both. And the people who would have been doing this study were not the COVID pandemic, would have been sitting just a few desks away from me. But what is quite interesting is that these two studies, although superficially quite similar, take quite a different approach. So the China UK Biobank study, the methods they're conventional conservative, and what is output is basically it's a survey of relative risks, okay, and they're related to your individual risk. So what is a relative risk? Well, they estimate the ratio of disease rates in exposed compared to unexposed individuals. Now, the study that I did with UK Biobank, it's trying to combine both the established methods with some of the newer methods in causal inference. And the output, in contrast, are the estimated proportions of disease that might be avoided by changes in lifestyle. So these are population attributable fractions. So what's an attributable fraction? Well, I picked up a established textbook for this, and they say that they are measures that attempt to assess the public health impact of an exposure. So already measures that attempt to assess it it's already sounding a bit vague. We will refer to the entire family of such fractional measures as attributable fractions. Okay, so there are many slightly different definitions of these things, and in many ways there are good reasons for this. The most commonly seen definition is this one, where the attributable fraction is the difference between the incidence rate in the exposed, i.e., minus, and the unexposed, i.u., given by this simple formula there. It's often written in terms of relative risk, where RR stands for relative risk. And if it's a proportional hazards model, that relative risk will be written in terms of a linear predictor eta. So here, it's e to the eta. But the basic idea is fairly straightforward. You're trying to assess the proportion of disease that is caused by an exposure or that you avoid by taking a drug. And this is where you get to the problems. So how do you estimate how much disease is actually caused by an exposure? And epidemiology will tell you that statistical associations do not indicate causation. A weak association could have many different indirect causes. There could be confounding, there could be reverse causality, where the weight loss is due to the disease, not causing the disease, for example. There could be differences in the population, genetic differences, for example. Many different things could be going on. So what do? Do you give up? Well, you might quite reasonably sort of give up or revert back to some more sort of conservative estimates. But the way I will proceed will be very much in the spirit of George Box, who says, well, all models are wrong, but some are useful. You might more accurately say, with enough data, all models are wrong. I thought I'd better put nearly back in there because, strictly speaking, there might be some that are correct. Okay, so what do we observe? We observe things such as your socioeconomic status, education, whether you get the disease or not, risk factors such as smoking and BMI. And a very simple and quite reasonable model would say that things like smoking and BMI, they're directly acting on your disease risk, whereas your socioeconomic status, your education, and those sort of things, they can modify your disease risk both through, say, exposure through workplace or where you're living, but they will also may well influence whether your risk of smoking or your BMI. So this model is not going to be exactly right, but it may be about right for most diseases most of the time. But what we're interested in is what would happen if we could, wave a magic wand and say, okay, well, in this population, if we could just stop everybody smoking and ensure everybody was at a medium sort of healthy weight, how would this change patterns of disease? How would this change the demand on healthcare services? And how can we use the observational data to do this? And that brings us on to the main chunk of what I'm going to talk about. So that's what we observe, and this is what we're interested in. And one approach that's very popular nowadays is Mendelian randomization. So here you use genetic information as an instrumental variable or a proxy for an exposure, such as high cholesterol. And the idea is that you find a gene that's associated with an exposure, and then mediated by an exposure, that gene is also modifying your risk of disease. And then providing that this model is correct and the gene is not changing your disease risk in some other way, then you can infer how strong that effect of the exposure is on disease. Okay, and you can do some simple statistical checks to at least ensure that your data is consistent with this model. So that's one approach, and that's becoming very popular. The alternative approach is to use the sort of methods of causal inference that you'll find in books by such as J. Pearl and others. So just to briefly go recap of this. So if Y is your disease state, Y equals 1 is disease, 0 if it's not. X is your risk factor, Z are your confounders. If you were using conventional Bayesian probability theory, you could use marginalization and then expand to see how the influence of the your risk factor would modify your be linked to your probability distribution for confounder Z. So that's standard probability theory, which most people are fairly familiar with. But the problem we have is that we want to consider a situation where we've intervened in some way. We're setting everybody to non-smokers, for example, and in that case, you've no longer got that confounding influence on the exposure. And so for those of you who are unfamiliar with this, the strategy is you consider the two different models, you identify the equivalent terms, and then you rewrite things using observable quantities. And this would lead in this case to what is a well-known formula, the adjustment formula. And the difference is that in the adjustment formula, the probability distribution for the confounders is no longer conditioned on the risk factors of what you're also working on. So that's great. So we can work this thing out, at least in principle. So the next question is, how do we summarize the consequences of this intervention? And this brings us back to attributable fractions. And there are many similar but distinct questions. So first of all, if everyone in the population were to, for example, stop smoking, how much will, within that population, the incidence of disease change. And this brings us on to things such as population attributable fractions, the excess fraction, the average causal effect. Another question you might ask is, well, if you individually were to stop smoking, how much will your disease risk change? And then here you're concerned with individual health and the effect of treatment on the treated. You may also ask, well, given that this person has died from lung cancer, how likely would this have been if they had not smoked? So this is the probability of the event would not have occurred but for the defendant's actions, or the probability of necessity. So you can start to see why there are many different, slightly different attributable fractions that have occurred, because there are several similar but distinct questions that you might reasonably ask. I'm going to concentrate on the top one. And so the first thing what one looks at is the average causal effect. So I'm looking at the probability of the disease within some age little t, and compare that with the probability of disease within some age little t, given that you've set everybody, say, to non-smoking. And if I just divide that through by the first term, then we get this an attributable fraction that ranges between, in principle, between 0 and 1. I'll come back to that. So if a non-smoker has, say, 0 risk of disease, then the attributable fraction would be 1. If, on the other hand, smoking had no effect on your disease risk, then the attributable fraction would be 0. So that's capturing the kind of notions that we'd like to. So we've got the adjustment formula that allows us to estimate things. We've got the attributable fraction. The next question is, how do we actually, evaluate all these terms? And so just a little bit of revision for people not familiar with this stuff. So in the middle is the thing that most people are most familiar with, which is the probability density function. So that would tell you the probability of getting a disease between age 100 and say 101 as the area under the curve. Okay, so most people are familiar with that. Survival function is also familiar to many people. So that's the probability of surviving disease up to a given age. And then the third thing on the far right is my favorite of all. It's the hazard function. And this tells you what many of us are more interested in, which says, given that you're alive today, what's the probability you're going to be dead within the next year or so? Or strictly speaking, within the next infinitesimal fraction of time, but in practice, a year or so is about right. And all three of these things can be related to each other. And you can calculate each in terms of the other in various different ways with different degrees of sort of complexity. But what most people don't know is that for most people and most diseases, they are sufficiently rare for most of the human lifetime. You can actually approximate this probability density function by the hazard function. So this is data from UK Biobank, where I estimated the probability of disease by a given age in the absence of any prior diseases. Now, if you have existing disease, it changes your substantive risk of getting unwell. But this is so without prior disease. This is your disease risk, and you can see that even by age 90, these are very, very low risks. It's just the problem is there are many, many, many different diseases, which makes it almost inevitable that one of these, that's going to get you. Now, fortunately, I'm not the only person to have noticed this. When I started working as a statistical geneticist last year, I came across this paper, which is very important in statistical genetics, and they made a similar observation, but in a different context, which is very reassuring because now there's at least 2 of us who suggested this. Okay, so that's the approximation I'm going to make, that the probability density function is roughly equal to the hazard function. A few other things to introduce. The cumulative hazard function is just the integration of the hazard function, or the area under the curve, if you prefer that. The survival function can be written as the exponential of minus cumulative hazard function. And the cumulative distribution function is just 1 minus survival function. And under this approximation, then we can approximate the cumulative distribution function as the cumulative hazard function. And this is great because it makes a lot of the maths very much easier. So just to summarize, so we've written our survival function in terms of a cumulative hazard function. And if we assume a proportional hazards model, then we're assuming we can write the hazard as a product of a baseline hazard, which is the same for everybody, and is usually age dependent or time dependent, and a factor that incorporates all your risk factors to do with your, say, smoking, BMI, etc. And that's the relative risk. So if you divide that through by your hazard at the baseline values, where the relative risk would be equal to 1, then you're left with that term there. Okay, so now we've got our attributable fraction. We know how to evaluate it in principle in terms of an adjustment formula, and we've got this estimate that simplifies things tremendously. And there's one last thing that I would like to do, which is to approximate the integrals with sums, because in UK Biobank data, for example, you've got 500,000 people. So even for smokers, where say 10% of the population are smoking, it's still 50,000 odd people. These are big numbers. So these are pretty good approximations, and it makes life a lot easier. So if you stick all those things in and cancel out a few terms, then this is what you're left with. The W are risk factors that you're not interested in. I've just put them in for completeness. And this is lovely, really, because this is directly very similar to what already exists in the literature. It's easy to evaluate. You can use your standard established methods of estimating disease risk with proportional hazard models that everybody is very familiar with and have done for years. But now you can estimate an attributable fraction that, in principle at least, is accounting for these correlations between various confounding factors. Okay, so that's the model, and I'm just going to very briefly show you some of the results, and then I'm going to finish. So these are attributable fractions ordered from highest to lowest. I think I've shown, and it's for both smoking and BMI combined. At the very top, unsurprisingly, you see obesity, which is reassuring that it's nearly 100%, because clearly if your BMI is above average, that's a necessary thing if you're going to be defined as being obese. But with that, and that's reassuring that the model is working. In red are diseases for which about half of all the diseases we see in our hospitals today could, in principle, be avoided by changes in lifestyle. Now, this is what an attributable fraction emphasizes you will not see from a relative risk. So for relative risks, you can have a relative risk of even say 20, be very high. But if your underlying risk of disease is very low, it doesn't really matter. Relative risks just don't tell you how big the burden of disease is in this sort of way. And as you go down, you can see that there are many different diseases with a very high proportion of cases that are potentially avoidable, according to this model with all the caveats that I mentioned earlier. And you can break this down, and you can look. I think my screen is frozen. I think the screen is frozen. I'm completely calm.
Escaping and trying.
Oh, there we are. And you can break this down by different types of diseases. So unsurprisingly, at the top, you've got diseases of the respiratory system, as you would expect for things like smoking. You've also got the nutritional and the metabolic disease, which is unsurprising. But then you also see things that, like diseases of the nervous system, which you may not have anticipated. So you get this different perspective that you wouldn't be able to see by looking at relative risks. And if you look at this, so this is now for all the diseases that I considered. Now you can see that some of these attributable fractions are negative. And you might say, well, what does that mean? Surely they can't be negative. Well, it turns out actually, providing they're small in magnitude, there's a clear interpretation of negative attributable fractions, but with the opposite effect. So instead of protecting against disease, they're causing disease and vice versa. But what this emphasizes, that if you look even at smoking, there's a considerable number of different types of diseases for which, if you stopped smoking, your risk, the numbers of cases that you'd expect to observe would increase. So by changing your lifestyle, you won't just simply change the number of diseases you'll see, you'll change the whole pattern of diseases that will be experienced. So looking at some of these diseases for which there is a protective association. You've got melanoma in situ at the top there. Going down the list, there is malignant melanoma of skin. Carrying on down the list, there's other malignant neoplasms of skin. Okay, this is a bit of a pattern emerging there. Inflammatory diseases of the prostate. Going down again, well, malignant neoplasm of the prostate. And I think there's another one there to do with the prostate. I can't see it. Hyperplasia of prostate. Okay, so again, there's a pattern emerging. It doesn't mean that any of these are necessarily protective associations, but there's a bit of a pattern there, and I think there's enough evidence to follow it up. Okay, so just to conclude on the results part, it appears that a substantial proportion of disease is caused by smoking BMI. It also appears that there can be some protective associations, and these may well point the way to sort of biological understanding and treatments. I should emphasize again that the results for any specific disease should be treated with caution, and these should be examined with expert biological and clinical input on a case-by-case basis. Regarding attributable fractions, I would argue that there are situations where a causal interpretation is meaningful and reasonable, and when the backdoor criteria applies, then simple approximations can allow attributable fractions to be estimated using conventional, well-established proportion hazard methods that are familiar to the majority of epidemiologists that are working today. And this approximation, I mean, strictly speaking, it's an approximation that improves for younger ages, but for most diseases, it is good for the lifetime of most people. Alternatively, you consider it as exact, but in the limit of a sufficiently low age. So I think I'm nearly finished. So it just remains me to say thank you to the Nuffield Department of Population Health for funding the work that led to this. And thank you to you for your attention.